Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 18th, 2025. So just 3 days ago. This paper introduces Franca, the first fully open-source vision foundation model that releases all its components, data, code, and weights, while matching the performance of top proprietary models like DynoVive 2. The paper is titled Franca Nested Matryoshka Clustering for Scalable Visual Representation Learning, and the implications for open-source AI are really significant. It tackles critical limitations like ambiguity in how models group features and positional biases that can distort a model's understanding. Also, the authors shared the official GitHub for Franca. The code and checkpoints aren't quite ready, but they've noted they'll be releasing them very soon. So you can go find the repository and give it a star to get notified when the full implementation drops. Alright, so this first figure gives a great overview of the whole project. At the top left, we see the core method, this nested Matryoshka style clustering. It's a clever design where the model processes an image's features at different levels of detail simultaneously, from broad strokes to fine-grained clusters. To the right, the diagram highlights their data strategy. They use publicly available internet data, unlike proprietary models, and the results at the bottom are really telling. Across different tasks like in-context learning and 3D understanding, Franca, shown in green, consistently matches or beats established models like DynoV2. Building on that idea of openness, this table provides a stark visual comparison. It lists several major vision models, like Metaclip, DynoV2, and of course Franca, and checks their public availability across key components. You can see Franca is the only one with green checks all the way down. They've released everything: the model, the code, the training data, and even the intermediate weights. These weights are basically snapshots of the model during training, which are crucial for reproducibility. This visual really highlights the transparency gap Franca is filling. Okay, so this next figure really breaks down how each of Franca's innovations contributes to its final performance. This is what's called an ablation study, where they start with a baseline model and add each new component one by one. The inner bar measures in context segmentation, which is how well the model outlines objects. We see the Matryoshka clustering gives a huge boost here. And the final step, RASA, a method that removes positional data to force the model to focus on content, also adds a nice gain. Every component provides a clear, positive improvement. So to understand one of those key components better, this image visualizes different masking strategies. Masking is a training technique where parts of an image are intentionally hidden, forcing the model to learn from the surrounding context. You see common methods like random or block masking, but Franca introduces its own method, called CyclicMask, shown on the far right. Instead of just hiding a fixed area, it circularly shifts the visible region. This clever trick prevents the model from developing a positional bias, essentially keeping it from learning that important things are always in one spot. And this plot really drives home the benefit of that Matryoshka clustering I mentioned earlier. What we're seeing here is K nearest neighbors classification accuracy. That's a test that checks how well the model can group similar images by comparing them to known examples. The horizontal axis shows what happens as we use smaller and smaller slices of the model's features. You can see Franca's performance, in green, stays remarkably stable. But DynoV2's accuracy just plummets. This shows how efficiently Franca packs useful information, maintaining quality even when its features are highly compressed. Alright, so this next plot dives deeper into that positional bias problem we talked about earlier. It uses a concept called entropy to measure it. In this context, low entropy means a feature is tied to a specific location, like only recognizing a dog's ear when it's in the top corner. High entropy means the model recognizes the feature anywhere. The chart shows DynoV2 has low entropy, but Franca's is much higher, demonstrating its features are more position invariant. This is a direct result of that removal of absolute spatial attributes technique. So in conclusion, this paper really sets a new benchmark, not just for performance, but for transparency. By using its novel techniques, like Matryoshka clustering, which efficiently nests visual features from coarse-to-fine, and that removal of absolute spatial attributes method, which helps the model focus on content, not location, it manages to match or even beat closed-source giants. It's a powerful demonstration that open, reproducible research can lead the way. That's all the time we have for this week's AI Research Roundup. Thanks for tuning in.